Welcome back to the Psyche and Singularity video series. I've been going over my book, Psyche and Singularity, Jungian Psychology and Holographic String Theory. If you've been watching, you already know what I'm trying to do here. But briefly, in the book, I am equating the psyche, or the self, with what physicists call the gravitational singularity, which includes a horizon, and especially the horizon of the universe, the cosmic horizon, where the past, present, and future are conserved. So, in the previous video, I went over the history of physics from Newton's theory to Einstein's special theory of relativity, to his general theory of relativity, and then to quantum mechanics. And I left off talking about the conflict between quantum mechanics and relativity theory, but especially general relativity, the theory of gravity, that physicists, ever since the discovery of quantum mechanics in 1927, were trying to reconcile it with Einstein's theory of gravity, and it was always ending up with catastrophic infinities, that it would lead to an infinite amount of energy in the quantum vacuum, which I will be discussing, and how string theory finally, at least mathematically, reconciled general relativity and quantum mechanics. And it is Leonard Susskind's holographic interpretation of string theory that I'm comparing to Carl Jung's theory of the archetype of the self, which is the psyche, the conscious self. What is that? I'm saying it is what physicists call the gravitational singularity, especially as described by Leonard Susskind. And it's the singularity in the center of the universe, which includes the horizon of the cosmos. But the singularity also exists at each point of the underlying quantum vacuum, as I discussed in the previous video, and also within black holes. There's black holes at every point of the quantum vacuum. It is theorized. There's a supermassive black hole in the center of every galaxy. There's medium-sized black holes strewn throughout each galaxy. The singularity is omnipresent, omnicentric. And so just to understand and appreciate the parallels between the physics of the singularity and the psychology of the self, which is what Carl Jung and his partner, the co-founder of quantum mechanics, Wolfgang Pauli, set out to discover, parallels between the laws of physics and the laws of psychology, which they thought it must exist because matter and mind both emerge from the same transcendental source, which they called the unus mundus, as well as the archetype of the self, the God archetype, and the one. So, picking up where we left off, the problem of uniting relativity theory with quantum mechanics is related to the problem of infinity, which is at the core of all the controversy around the concept of a singularity, because it's defined as a point of infinite gravity and zero volume. Infinite gravity, now you're outside the laws of physics, you're outside of space and time. Is that really physics anymore? A lot of physicists think it is not. You've now entered into the realm seemingly like theology, and I'm saying yes, that actually is the case. But that doesn't mean that it is unscientific and should be discarded. Although, and that's a controversy between physicists. Some accept the reality of the singularity, which is this undefinable, infinitely powerful, and omnipresent entity. And then some physicists who say, no, there must be a problem with Einstein's theory of general relativity because it points to this singularity. It spells it out very clearly. And such a thing is impossible. Einstein himself thought singularities were impossible. So, I'm going to briefly go over the history of the attempts to combine special relativity and general relativity with quantum mechanics. So the four forces of nature, the electromagnetic force, the strong nuclear force, the weak nuclear force, and gravity. The goal that physicists strive for is to unite our understanding of all four forces so that they can all be described with one law of physics. Why should you have one law of physics, quantum mechanics, that describes the electromagnetic force and the weak and strong nuclear forces, and then another language, general relativity, to describe gravity. There should be one law of physics that describes nature at every scale and at every speed. That's what string theory successfully does in its mathematical descriptions, although those descriptions can't be empirically verified. The strings are too small to see, and the compactified dimensions of extra dimensions of space are too small to see. We're going to get to that near the end of this video. So how can you combine quantum mechanics and relativity theory? The first attempt was to combine quantum mechanics with special relativity, which Einstein discovered in 1905, which we discussed in the previous video. It has to do with the speed of light, stopping time, the absolute speed of light. Nothing can go faster than light, no matter how you measure a light beam, no matter how fast you are going or the source of the light is going, you will always measure it to be going at 186,000 miles per second. So if the speed of light is constant, then space and time must bend and twist to maintain that constant speed of light. The measurement of the speed of light will always come out the same. Therefore, the faster you move through space, the slower you move through time, and the more contracted you become in the direction of your movement through space. So I'm going to just read a little bit here. In the early 1930s, they tried to invent quantum field theory. So quantum field theory describes the forces of the quantum realm as the emission and absorption of particles. So one form is quantum electrodynamics, which describes the electromagnetic force, which is light, as photons in an atom being passed back and forth between the orbiting electrons and the nucleus of the atom. This back and forth rapid passing of a photon is the electromagnetic force. In one of Brian Greene's videos, he showed a video of himself passing a baseball back and forth to himself, and the more they passed it back, this one self was getting dragged in towards, they were getting dragged towards each other. So that is quantum field theory. Leonard Susskind explains photons are the ropes that tether the electrons to the nucleus. And then quantum chromodynamics describes the strong and weak nuclear forces, and according to Susskind, with a quark replacing the electron and a gluon taking the place of the photon. So the problem is, as we discussed in quantum mechanics, Heisenberg discovered the Heisenberg uncertainty principle, a wave of probability. When an electron or a photon, any quantum particle, behaves like a wave when it is traveling through space unobserved. What kind of a wave? As we discussed with the two-slit experiment, a wave of probability. What is that? It's the probability for where the particle will appear in that wave were someone to observe it, or were a measurement to be made on it. Most likely at the peak of the wave, but it could be anywhere within the wave, and the ends of the wave stretch out to infinity. There's an increasingly small chance that it could appear anywhere in the universe, but most likely at the peak of the wave or the valley of the wave. Because what you do is you take that wave, Schrodinger's wave function, and you multiply it by itself. You square it, so that the peaks will become twice as high, and the valleys will just become like other peaks, because a negative times a negative equals a positive. So you'll always get a positive probability for where the particle might appear where you observe it. So in the quantum vacuum, underlying every point of three-dimensional space, you have all of these virtual particle-antiparticle pairs. All of the potential positions of each quantum particle, and I don't understand I understand as much as I can glean from reading the experts and watching their videos, but the mathematics of quantum physics indicates that each particle creates its own antiparticle pair, its own antiparticle, and that as soon as they emerge from nothingness or empty space, the quantum vacuum, then they recombine and annihilate each other. and that each, for example, in the electromagnetic force, as photons are passing back and forth between the electrons and the protons and neutrons, the nucleus of the atom, the trajectory of each of those photons isn't in a definite state until it's measured. And so there's an infinite number of possible paths the photon could take. And each of those potential paths it takes creates its own antiparticle. The most important point for what I'm trying to do is to explain that quantum mechanics indicates there's an infinite amount of energy in the quantum vacuum at every point. This is the catastrophe that they were trying to avoid, because you can't do math when you've got infinities popping in. It throws all the predictive power of the equations out the window. So I'll just read a little bit here from Susskind. So according to Susskind, the fluctuations of the quantum vacuum are created by the fact that all possible paths contribute to the probability for the particle to go from A to B as a result of the Heisenberg uncertainty principle. So there's infinite numbers of paths, and so this led them to the discovery of the quantum vacuum in the 1930s. So I'm going to read a little bit here. Leonard Susskind recalls on his first day as a physics professor in 1967. He walked into a classroom, and there were some major league hitters in the world of physics: Roger Penrose, Dave Finkelstein, and Paul Dirac, who had developed quantum field theory in the 1930s. And according to Susskind, Dave was arguing that the vacuum is full of zero-point energy and that this energy ought to affect the gravitational field. Dirac didn't like vacuum energy because whenever physicists tried to calculate its magnitude, the answer would come out infinite. So then in the 1950s, to try to tame these infinities, they came up with a concept called renormalization, or a mathematical technique called renormalization. And then, according to Heinz Pagels, who wrote The Cosmic Code, another physicist, he said if someone could actually put on an infinite amount of weight and then reset the scale by an infinite amount to give a finite weight, then one gets an idea of the amount of cheating or renormalization required in the calculational procedures of quantum field theories. So it nevertheless worked. It would renormalize their equations, get rid of the infinities, and then they could successfully combine special relativity with quantum mechanics. And that led to quantum electrodynamics and quantum chromodynamics. But the problem came when they tried to combine quantum mechanics with general relativity. Then they couldn't use their tricks anymore. And according to Michio Kaku, he says, when you do try to combine quantum mechanics and general relativity, you get an infinite sequence of infinities, infinitely worse than the divergences of Einstein's original theory. This is a nightmare beyond comprehension. So, Michio Kaku, it seems to me, agrees with Leonard Susskind in his interpretation of the universe as a meaningless, impersonal, massive ball of unconcerned energy. And so when you have these infinities cropping up, the physicists, it seems to me, who don't believe in any kind of a sentient universe, get rightfully suspicious, because it does start to sound like theology. Stephen Hawking commented upon this point in his A Brief History of Time. He talked about the Pope Pius XII, when he said that the Big Bang theory that George Lemaitre, the Jesuit priest, came up with using Einstein's general theory of relativity, it indicates it's evidence of creation of the universe from the hand of God. And then after that, apparently, a lot of physicists said, yeah, it does sound like that. Therefore, the idea of a gravitational singularity must be wrong, because there's no God. Therefore, there cannot be a gravitational singularity. So my point here is, I'm not trying to compare myself as a physicist to Kaku at all, but as a philosopher, what appears to him as a nightmare beyond comprehension is a dream come true for me, because there's been this kind of battle between belief in a sentient universe, and that sentience itself is not a byproduct of matter, but inherent to the cosmos. And physicists who generally, not all of them, but many physicists take the materialist philosophy that life comes from matter, it's not an essential part of the cosmos. So now we're getting down to the quantum vacuum, which is the ground of being itself, and it supposedly has an infinite amount of energy at each point. Each point is a singularity. So if the psyche is the singularity, that implies an absolutely conscious cosmos. That would be a nightmare beyond comprehension to someone who wants to perceive the cosmos as an inert, impersonal energy source. So we'll be coming back to that concept again and again throughout this book, because it is this controversy about the existence of infinite energy. Does it exist? I'm saying it does, but it's not material anymore. It's spiritual or psychic or archetypal. When something has infinite energy, now it's in the realm of the archetypes. All right, so I'll just continue going through this, the pages here briefly. This is kind of a guide to those who have already bought the book, Psyche and Singularity. I realize that most people who watch these videos aren't going to buy the book, so I hope you can at least get the main gist from these videos. All right, so John Griven, going back to John Griven, says that empty space may be made up of black holes the size of the Planck length packed tightly together. So the Planck scale, 10 to the negative 33 centimeters, I believe. It's this ultimate smallest size according to the laws of physics. I don't understand the laws of physics that led them to this constant of nature, but that's the smallest size they say you can get. And the singularity is smaller than that. It's infinitely small. It contracts into itself infinitely. But that is what the trying to combine general relativity and quantum mechanics leads to the idea that maybe at the ground of being, everything is made of these miniature black holes. So when Einstein realized that, he didn't like Carl Schwarzschild's paper pointing out that general relativity points to the existence of black holes. Einstein didn't like that. And now here he is. He didn't like quantum mechanics for the reasons I explained in the previous video. And now he's seeing that quantum mechanics is bringing up the thing he didn't like about his own theory, which is the existence of singularities. Much worse. It's not just a big enough star that collapses into itself. It's at every point underlying three-dimensional space. So on May 10th, 1939, he published a paper where he asked, or he pointed out, there arises the question of whether it is possible to build up a field containing such singularities with the help of actual gravitating masses, or whether such regions do not exist in cases which have physical reality. So he said, no, they don't. If they're not physically real things, this whole concept of singularities, especially at every point of a quantum vacuum, Einstein rejected the whole thing. However, ironically, that same year, on September 1st, 1939, which was the very day World War II started, Robert Oppenheimer, he published a paper along with one of his graduate students, and he showed that according to quantum mechanics, when a star burns through its nuclear fuel, the gravity of that star will collapse it into a singularity. And he used the word singularity to describe that in that paper. I think it's interesting to note that that was the first day of World War II, and then Robert Oppenheimer effectively ended World War II because he was the chief scientist of the Manhattan Project, which developed the atomic bomb. So the very first day when Hitler invaded Poland, September 1st, 1939, Oppenheimer published a paper pointing to the singularity in a black hole after a star burns through its nuclear fuel. And then he ended World War II by heading the program that created the atomic bomb. And he famously quoted two verses from the Bhagavad Gita, the most famous of which is Krishna telling Arjuna, showing him his universal form that devours everything. Now I am become death, destroyer of worlds, or now I am become time, destroyer of worlds. I'll return to that, but if you believe in synchronicity, meaningful coincidences, which connect the material world with the world of meaning, as Carl Jung believed in and Wolfgang Pauli, and as I believe in, then there's some kind of a historical synchronicity about Robert Oppenheimer and his relation to the first and last day of World War II. That paper that Robert Oppenheimer published in 1939 also showed how certain stars would not collapse all the way down to a black hole. They would become a white dwarf, a star like the size of our star in our solar system, which is, the sun is 1,000,000 times larger than the Earth. After its nuclear fuel is burned out, it will collapse down 1,000,000 times to the size of the Earth. But you imagine all that same amount of mass concentrated in a much, much smaller sphere. The gravity would be intense. If it was a little bit bigger, then the electrons in all of the atoms would be pressed into the nucleuses of the atom, and the electrons and the protons would cancel out, leaving only neutrons. So that's a neutron star, an incredibly dense ball of neutrons. But according to Susskind, if our sun was about 5 times the size it is, it would collapse all the way down to a singularity. All right, so we're going through this historical timeline of the concept of the gravitational singularity. We left off with Oppenheimer's paper, the first day of World War II, 1939, when he described how a star collapses into a black hole. Then, in 1948, the Dutch physicist Hendrik Casimir discovered a way to detect experimentally the theoretical vacuum energy. So he reasoned that each of these particle-antiparticle pairs also manifests as waves of probability, and some of these waves would be longer than others. So if you put 2 metal plates very close together, then some of those waves of probability would not be able to manifest between them, and they wouldn't exist, but they would exist outside of those 2 plates. There'd be more energy outside the 2 plates than inside, and it would push them together. It would have an empirically measurable physical effect. And that experiment was conducted, and the 2 metal plates were pressed together, thereby providing empirical evidence that the quantum vacuum energy is real. It's an experimentally verified physical reality. So it sounds like science fiction or mysticism, but there is such a thing as the quantum vacuum. And the mathematics of quantum mechanics and relativity theory indicate it has infinite energy at each point, which is, according to Kaku, a nightmare beyond comprehension. But if you're equating the psyche with the singularity, as I am trying to do, then you see the psyche is present everywhere, which is my main point. And it's also something that Carl Jung believed, Wolfgang Pauli also believed, and so many religions from the past and philosophies, Plato, the Vedanta philosophy, St. Augustine, as we'll see in subsequent videos, this the belief in a psychic cosmos is an ancient one, and it is resurfacing thanks to 20th century physics. So after Hendrik Casimir came up with the empirical test to prove the existence of the quantum vacuum, jumping ahead to 1964, 2 American radio astronomers in New Jersey, Arno Penzias and Robert Wilson, working for Bell Laboratory, discovered the cosmic microwave background radiation, the echo of the Big Bang. They were trying to discover, where's the static coming from this big horn antenna. Bell Labs said, there's static, we're picking up too much static over the phone, can you discover where it's coming from? They did. It's coming from everywhere, every point in the sky, day and night at a constant rate. And they kind of stumbled upon this discovery, and they were given Nobel Prizes for it. It's the echo of the Big Bang. In 1927, Lemaitre came up with the idea that the according to general relativity, space is expanding, therefore in the past it must have been contracted. Far enough back in the past, it was contracted to a single point, which he called the primeval atom. And now in 1964, there's evidence for this explosion of that primeval atom. That's the cosmic microwave background radiation. Then in 1965, Roger Penrose and Stephen Hawking used general relativity to prove that so Roger Penrose proved Robert Oppenheimer's former claim that a star of sufficient mass would collapse into a singularity. And then Stephen Hawking said, that's interesting. What if we reverse the time direction of Penrose's work? Instead of a star collapsing toward a singularity, it shows a star expanding away from a singularity, which is the same as a Big Bang. It's an inside-out black hole. So that's where he began his claims to fame about masters of knowledge of black holes. And then finally, in 1967, John Wheeler, another American physicist, he coined the term black hole. So people started calling these mathematical objects black holes. Then, after Hawking helped to champion the idea of a gravitational singularity in black holes and at the Big Bang, he later reversed himself. As he explains in A Brief History of Time, he says, "It is perhaps ironic that having changed my mind, I am now trying to convince other physicists that there was in fact no singularity at the beginning of the universe. As we shall see later, it can disappear once quantum effects are taken into account." Okay, so then he says, in 1981, my interest in questions about the origin and fate of the universe was reawakened when I attended a conference on cosmology organized by the Jesuits at the Vatican. So here is how Stephen Hawking got rid of the gravitational singularity. He said, according to quantum mechanics, something that small will become, it's a wave of probability. So it's not a point of infinite gravity. It's a wave of probability, but this wave of probability is unique because each point in this original wave of probability does not represent an individual particle, it represents an individual universe. So to get rid of the singularity at the Big Bang, to get rid of that pestering infinity, he came up with the idea of an infinity of parallel universes. So, and I point out in the book that whenever physicists try to eliminate infinity from one of their equations somewhere, it seems that it pops back up oftentimes at an exponent of itself. Infinity times infinity, as we saw Kaku point out, when they tried to combine quantum mechanics and general relativity. It was infinitely worse than when they tried to combine special relativity and quantum mechanics. So this was the way Hawking tried to get rid of the singularity. Now it's a wave function of the universe, and each point in that wave function represents a parallel universe. This harkens back to 1957, when the physicist Hugh Everett III came up with the first theory of parallel universes based on quantum mechanics. He said, well, what happens to all the points in the wave of probability that don't manifest when it is measured? He said they each do manifest in a parallel universe. The only difference between one and the other universe being the position of that one particle in that one wave of probability. And so there's an infinite number of parallel universes, each universe corresponding to a different position of one particle in one wave of probability. So it's ever so finely sliced differences, but if you stretch that out to infinity, it becomes enormous differences. And they literally believe there's a parallel universe where I'm giving this video right now. Everything's absolutely the same except for the position of one particle somewhere, and everybody else. There's that many universes, which seems to me like theology also. And in fact, there are plenty of theologies that talk about parallel universes, especially the Vedanta, the Vaishnava Vedanta theology, which says that each universe is like a bubble breathing out of Mahavishnu. So we will be talking about that, but you see how the mathematics of 20th century physics, it's reinventing or rediscovering these ancient cosmologies. Kaku explains that the difference between Hawking's parallel universes theory and Hugh Everett's is that Hawking described the wormholes connecting the parallel universes, whereas Hugh Everett III did not. Okay, so I will leave it at that. Those were the attempts to combine quantum mechanics and general relativity, and it ends up with black holes and black holes at each point of the quantum vacuum, which seems to be a very painful thing to deal with if you're a mathematical physicist. And they try to get rid of these infinities using techniques like renormalization and other techniques. In the next video, I'm going to describe the emergence of string theory, and finally Leonard Susskind and Gerard de Hooft's holographic version of string theory. And that will conclude the history of the gravitational singularity, enough for me to make sense out of my equation of the psyche with the singularity, which is based on Carl Jung's equation, psyche equals highest intensity in the smallest space. So in the next video, we'll be going over the birth of string theory. Thank you for watching.